Good day, students. I am Dr. Monika Khetarpal. I am Associate Professor of Physics in Government Dongar College, Bikaner. Today I am going to deliver a lecture of MSc Final Physics, and the topic is superconductivity. Today I will discuss the thermodynamics of superconducting transition. The thermodynamics of superconducting transition is based on Misner effect. What does Misner effect states? Misner effect states that inside a superconductor, the magnetic field will be zero. But when the material become normal, then there will be penetration of magnetic field inside as well as outside the superconductor. Now, since Misner effect suggests that the transition between normal and superconducting state is thermodynamically reversible, just in the same sense as the transition between liquid and vapor phase of a substance is reversible under the condition of evaporation. That means, what does this say? Just as we are evaporating solid, then a gaseous state is formed. And we can also do reverse process. Misner showed that this transition is reversible. That means a normal state can be converted to a superconducting state, and similarly a superconducting state can be converted into a normal states. Thus, we can apply the same type of thermodynamics as we are using in liquid vapor phase transition. So here I am using the same thermodynamics for our superconducting state. In this condition, I am taking the superconductor, which is type first superconductor. As we already know that for type first superconductor, magnetic field is zero inside the superconductor. That means there is a completely Misner effect is followed here. That means B must be zero inside the superconductor. Now I am writing the internal energy density in the presence of magnetic field. This density is given by the second law of thermodynamics. We know that the expression is du is equal to TdS plus HdA. U being the internal energy density, T is the temperature, capital S the entropy, and M is the magnetization, H is the strength of magnetic field. I have written this expression in the presence of magnetic field. Now I am comparing it with the gaseous state expression. In the gaseous state, we know that internal energy density expression according to the second law of thermodynamics will be du is equal to TdS minus VdV. Here P is the pressure, V is the volume, T being the temperature, and S is the same as here entropy. Now I have written the internal energy density in the presence of magnetic field and for the gaseous state. And I have arrived two equations, first and second. I am comparing first and second expression. Here I got that P replaces minus H and V replaces M. The first term in these two expressions, TdS, is the same. Now we know that when we are considering thermodynamics for a liquid vapor phase transition, we write Gibbs free energy formula to be equal to G is equal to U minus Ts plus PV. Here I have already obtained the value of P and V by comparison of these two expressions. So substituting in spite of P minus H and in spite of V M, I got the expression of Gibbs free energy as G is equal to U minus Ts. minus Hm. This is the Gibbs free energy in the presence of magnetic field. Now what I am doing? I am differentiating my expression. That is, I am finding dg. So I got dg is equal to du minus differentiating the second term. As there are two factors t and s, I will get two terms du minus ts minus sdt. Now differentiating hm, I first get h differential of m minus m differential of h. Now here I have used my first equation where I have written du is equal to tds plus hdm. So what is the value of du? It is tds plus hdm. So this term cancel out and I got my expression dg is equal to minus sdt minus m dh. Now I am considering that my temperature is constant. For a constant temperature, variation in time is considered, a variation in temperature is considered to be 0. That means putting dt to be 0, I got dg is equal to minus m dh. This is the expression of change in Gibbs free energy. dg is equal to minus m dh. Now, this is the general expression of change in Gibbs free energy. First of all, I will solve this expression for normal state and then I will solve it for superconducting state. So let's see what change occurs in both states. Initially, I am taking my state to be normal. That means my temperature is below Tc. In this condition, material will be in the normal state. Now I am assuming that my normal state material is non-magnetic in nature. So if it is non-magnetic, here in this general form of expression, m will be equal to 0. So writing the Gibbs free energy in the normal state as Gn, I have replaced G by Gn for normal state. So the fifth expression can be rewritten as dGn, m is 0. So this side, that means right hand side, is equal to 0. dGn equal to 0. Integrating this expression, I get Gn at a particular temperature T, H, this is equal to Gn T 0. What does this show? That Gibbs free energy of unit volume of specimen in the normal state is not changed by the application of magnetic field. I have already taken that temperature is kept constant, so I am writing in these two expressions capital T. And in the normal state, so we can conclude that there is no variation in the Gibbs free energy by the change in magnetic field. This is for the normal state. Now moving over to my another state. My another state is superconducting state. Since we know that superconductor follow Misner effect, and that means B must be equal to 0. We know that B is equal to H plus 4 pi M. Putting B to be 0, we get M to be equal to minus H upon 4 pi. Since we know the value of M, I am putting the value of M in my general expression of change in the Gibbs free energy. dG is equal to minus M dH. Substituting M, I got dG is equal to H upon 4 pi dH. Now I am integrating my expression as temperature is kept constant. Variation is in the magnetic field. I got Gibbs free energy of superconducting state GSTH is equal to GST0 plus Integrating this, I got h square upon 8 pi. Gs means the Gibbs free energy of superconducting state. This is the Gibbs free energy of superconducting state at temperature T, and one magnetic field is H. This is the Gibbs free energy of superconducting state at temperature T in the absence of any magnetic field. So from here we can see that with the application of magnetic field, there is an increase in the Gibbs free energy of the specimen. And the increase is by a factor h square upon 8 pi. But we have already shown that in the normal state, there is no change in the Gibbs free energy by the application of magnetic field. Hence, in the two states, the variation of Gibbs free energy is totally different. Now, what we are going to do, we are finding a relation between the Gibbs free energy of normal state and superconducting state. Here we have derived the relation between the Gibbs free energy of normal state at two different fields, and similarly the Gibbs free energy of superconducting state at two different fields, that is h equal to 0 and at a particular magnetic field which is equal to h. So for this purpose, I am rewriting my expression for superconducting state for a magnetic field which has a value h equal to hc. I am rewriting my expressions. Firstly for normal state, I have substituted h equal to hc, and similarly here I have for superconducting state I have taken h equal to hc. So I get GSTHC is equal to GST0, and in spite of h I am rewriting it as hc. I got this expression. Now since what is hc? Hc is the critical field. What is critical field? Critical field is the value of magnetic field at which there is a transition from normal state to superconducting state. That means it is the point where both states can occur. That means Gibbs free energy of normal state will be equal to the Gibbs free energy of superconducting state. This is the condition of equilibrium. This T is kept constant. I am writing it as Gibbs free energy of normal state at a temperature T, and magnetic field we have taken Hc. This must be equal to Gibbs free energy in superconducting state at that particular temperature T, and field is Hc. So this is the condition of equilibrium. I have used this equilibrium condition and the ninth expression to rewrite my equation 7. Since here I have GSTHC, this is the expression, and what is GSTHC equal to? From this expression it is equal to GNTHC, and from ninth expression GNTHC is equal to GNT0. So in spite of this I have written GNT0 and the right hand side being the same. So I got the difference between the Gibbs free energy in the normal state and superconducting state. In the normal state, Gibbs free energy is GNT0, and in the superconducting state I have written it as GST0, and the difference is equal to Sc square upon 8 pi. Here the temperature in both states is kept constant T, and the magnetic field in both states is the 0. This is the basic equation which was obtained by Grotter and Casimir. So we have today derived the change in the Gibbs free energy in the normal state and superconducting state. Knowing the Gibbs free energy, we can find out the specific heat of the system. In my next lecture, we will determine the difference in the specific heat of the system.